In the last video, we developed the kinematics leg of the Tonti diagram for the bar. In this video, we'll develop the equilibrium leg. Before we do that, we need to review the fundamental theorem of calculus, which says that the integral from a to b of f prime of x dx is equal to f of b minus f of a. So let's take our bar that's fixed at the left end with the force of p hat of x applied axially with the force F bar at the end. Let's cut out a piece of this bar between arbitrary points x1 and x2 and draw a free body diagram. So the free body diagram has the external force in it, P hat of x, and it also has the internal axial force, F of x2 and F of x1. So if we sum the forces, we get f of x2 minus f of x1 plus the integral from x1 to x2 of p hat of x dx equals 0. Now if we apply the fundamental theorem of calculus, f of x2 minus f of x1 can be written as the integral from x1 to x2 of f prime of x dx, and then plus the external force term. And because the integral is linear, we can bring the two terms together like this. And since x1 and x2 are arbitrary, we didn't pick them based on anything. If the integral is 0, that means the integrand must be 0. So we have f prime of x plus p hat of x equals 0. So we can now build up the right leg of the Tonti diagram. F p hat is related to f by minus d by dx. And we see that the minus d by dx takes the place of b transposed in our truss Tonti diagram. We also have the other boundary condition, f of L equals f bar. So what remains is what connects epsilon to f. This is the constitutive equation. And from undergraduate mechanics, we know that that relationship is EA. So that completes the Tonti diagram. And now we see the features that we talked about in the beginning, that derivatives take the place of matrices, and we have the two additional boundary condition legs.